Okay, so this is a presentation on Essential Knowledge 2.1c6, the inverse chain rule. So the description given is the derivative of an inverse function can be found using the chain rule if the derivative of an inverse function exists. So the problem we have is the derivative of an inverse function, and a solution that we have is a chain rule. So for review, an inverse function is a function where all inputs equal the outputs of another function, and all outputs equal original inputs. So we can think about the original function being the function given, and then the inverse being the inverse of that function. So for example, f of x is the original function, and f inverse of x is its inverse. And f of 1 equals 0, f of 0 equals 1, and from this relationship we can distinguish that f of inverse of x is always going to equal x. So if we apply the chain rule is the derivative of f of g of x is equal to f prime of g of x times g prime of x. How is this used for inverse function? Well, when f and f inverse are composed, f of inverse of x is equal to x. If we want to take the derivative of both sides, we get this, and we know that the right side is going to equal 1, and the left side we can actually apply the chain rule. So if we do apply the chain rule, we get f prime of f inverse of x times the derivative of f inverse of x equaling 1. If we want to find the derivative of f inverse of x, we just have to divide both sides by f prime of f inverse of x. The derivative of f inverse of x is equal to 1 over f prime of f inverse of x. So therefore, to find the derivative, we need f prime of x, f inverse of x, and the derivative, this relationship right here. For example 1, we have f of x equals tangent of x, and we define the derivative of f inverse of x at x equals 1. So we know that f prime of x equals secant squared of x, and f inverse of x is equals to arctan x. Okay, so for this first example, we have f of x equaling to tangent of x, and we need to find the derivative of f inverse of x at x equals 1. So using prior knowledge, we know that f prime of x is equal to secant squared of x, and f inverse of x is actually equal to arctan of x. So now in order to find the derivative of f inverse of 1, we can use the relationship from earlier. So we set it up as 1 over f prime of the input f inverse, and the denominator will actually turn into 1 over secant squared of arctangent of 1, since f inverse of x is really just equal to arctan of 1, and then the derivative is secant squared, so we put arctan of 1 into secant squared. Now all we need to do is just simplify it. So arctan of 1 is equal to pi over 4. We know that cosine of pi over 4 is root 2 over 2, so secant is equal to 1 over cosine, which is going to be the reciprocal of cosine. So the reciprocal of root 2 over 2 is just 2 over root 2, and then we square that quantity. So when we just simplify, we just get 1/2 as our final answer. So 1/2 would be the derivative of f inverse of x at x equals 1. To check, recall that the derivative of arctan is actually equal to 1 over 1 plus x squared. So using that, if we plug in 1 for x, we do also end up with 1/2. So that's a really simple way to check, and we can also use this principle for arc sine and arc cosine if we do know those derivatives as well. Two problems here that we're going to solve for is the first one, which is a standard one, f of x is equal to e to the power of x. We need to find the derivative of f inverse of e. And then the second one, which is more challenging, is the function f of x equals x to the power of 4 minus 3x squared plus 2. And we need to find the derivative of f inverse of 1 using implicit differentiation. So pause this video and try to solve these two problems. Alright, for the solutions for the first one, to find the inverse of f, we can set f of x equal to y, and then we can solve for x, and we take the natural log of both sides to get x by itself, and then to just find our inverse, we just set x equal to f inverse, and we replace the y with x. So f inverse of x is equal to the natural log of x. And we know that the derivative of f here is just going to be e to the power of x. So we have what we need, and then now we can just apply the relationship that we know. So the denominator turns into 1 over f prime of natural log of e, and we know that the natural log of e will just always be 1, and then we get 1 over f prime of 1, and since f prime is e to the power of x, we just get 1 over e to the power of 1 as our answer, which is just 1 over e. So that's how we do the first one. For the second one, we actually want to let y equal the inverse of f of x, and we know from the relationship from the review, f of f inverse of x is going to always equal x. But since we let f inverse of x equal y, we can actually do f of y equals x instead, which is all equivalent. So since we're setting x equal to y, we know that f of y is going to actually equal y to the power of 4 minus 3x squared plus 3. And then we can also set that equal to x, since all we're doing here basically is just setting a lot of relationships and from step by step, so we can find an equation that we can take the derivative of implicitly. So we did do that here. So we have y to the power of 4 minus 3 squared plus 3 equals x, and then now we can just solve for the derivative implicitly, and by taking the derivative, we end up with dy over dx is equal to 1 over 4y cubed minus 6y. And you can see the steps that I did here should be kind of review. And then we need to recall that we set y equal to the f inverse of x. So because we did that, we have to find f inverse of 1, since we're dealing with y's in this equation, but we need to find what y equals. So to do this, we know that f inverse of 1 is going to equal the x value when f of x equals 1, since this function is an inverse of the original function f. Alright, so by just guessing and plugging in, we know that f of 1 is going to equal 1 to the power of 4 minus 3 times 1 squared plus 3, which actually gives us 1. So we have y equaling f inverse of 1 equaling 1. Okay, so that means that y is going to equal 1. So because y equals 1 now, we have a value for y, and we can plug in that value in our implicit differentiation equation. So now to solve for the final answer, we have dy over dx at y equals 1 is equal to 1 over 4 times 1 cubed minus 6 times 1, which just equals negative 1/2. And if we do use our relationship that we went over with at the beginning, we would also get negative 1/2. So there's actually two ways we can find the derivative of an inverse function at a certain value x. But me personally, I think using the relationship is way more efficient if you do remember it. But you can also do it implicitly if you forgot how to find the relationship. But remember, in order to find the relationship, you need to know this relationship right here, f of f inverse of x equals x. So if you know this, you're set and you know how to find the derivative. So thank you for watching.